minus 4 to the n, take away 1, must be divisible by 3 for all natural numbers. So, let's see if we can at least write a base case and write an inductive hypothesis. This one's actually kind of gnarly. It's cool. If I keep saying that, eventually you'll believe it. It's like, yeah, Dave, this is really cool. Here's the question. What the heck do we mean when we say it's divisible by 3?
Comes out even if you divide by 3.
So you divide by 3, that's one way to think about it.
No remainders, yeah, same thing.
Same thing.
Whole number.
It's 3 times something?
3 times something. Right? And that's actually going to prove to be the important way for us to think about this. So what's our base case? What's the smallest natural number?
1.
So our base case is, right, is 3 divisible by 3? Absolutely. And we know that because it's 3 times 1. Right? So when you divide by 3, you'll get a value of 1 with 0 remainder. Now, what would our inductive hypothesis be? Says true. So did anyone get anything written down here?
4 to the k plus 1.
4 to the
minus 1.
4 to the k minus 1.
Equals 3k.
Ooh, equals what? Is that you?
Yep.
3k. 3 times the natural number?
Interesting. Does everyone see why I'm saying 3k?
Uh-huh.
In this particular case, it works. Let's try a second case. Equals what? Good thing it's not 3 squared. Keep it honest here.
16 minus
4 squared minus 1 is 16 minus 1 is
15.
right? So it won't necessarily match the k, right? Though that was a good observation, certainly from our base case. So instead of saying 4k minus 1 equals 3k, what would you say? It equals 3 times? There's got to be some number. I'm just not going to call it k, I'm just not going to call it n.
Yeah,
Now you figure we probably could. It's going to be an integer value, right? Whatever. Like, Josh, that takes us back to the overhead up front that said introduction to. All right. And then you figure p is going to be an integer value, presumably some positive integer value, right? But I'm not going to prove that right now because I haven't thought that hard. All right, so that's our inductive hypothesis. Quick question. Y'all buy that?
Mm-hmm.
Right, I'm just manipulating my inductive hypothesis a little teeny bit here, right? And we'll see why in a second. So, what would our k plus first statement be?
Replace k with k plus 1.
Right, or well, rather than k, replace n
Oh, sorry.
with k plus 1. So we need to show minus 1 equals what? 3 times something. What do you want to call the next something? Call the first something P. I often would call the next one Q, right? Four to the k plus 1 minus 1 would then be divisible by 3. Right? And Q is going to be another whole number. So what do we do next? We screw around with the left-hand side and see if we can make this work. Now, this goes back to Math 60. What two things could you multiply to get 4 to the k plus 1?
4 to the K,
4 to the k and 4 to the 1, right? Good old-fashioned addition of exponents. So let's come to the back chalkboard. The only reason I'm still doing this is because John has the tripod doing it, right? Because there's really plenty of room to make. Let's just do it up.
One of you's next week.
So what do we have? 4 to the k plus 1 minus 1. All right, we just have to figure out what the heck Q would be in order for this to work. So how are we going to rewrite? Well, actually, we aren't even writing that. So how are we going to rewrite the 4 to the k plus 1? 4 to the k times 4 or 4 times 4 to the k. Either way we write it should be acceptable. Let's do that. Let's do this. Oh, sorry, dude. So it's 4 times 4 to the k minus 1. What do we know about 4 to the k?
4 to the k equals 3p
3p plus 1. So what do you suppose we can do with that? Go nuts. 4 to the k is 3p plus 1. What do you typically do with a statement like that? You distribute the 4, combine like terms, right? Good old-fashioned Math 60 kick in for us again. Plus 4. Agreed like terms. Any common factors? Right? And that's what we want. We want a 3 in there. So of course this would be 3 times. So what does that mean?
Q is equal to 4p plus 1.
And you're done. We figured out a value for Q, right, for the k plus 1. We want to show that it's equal to 3Q. Put the left-hand side, we screwed around with it. That's our Q, 3 times something. Cool. See how much fun this can be? I'm thinking, so long as nobody has homework tonight, you're going to take that exercise sheet and you're just going to have a blast this evening. Now let's go to Shu's example from last week. This one gets a little bit gnarly. Not that gnarly. All right, but the statement that we want to prove is that 2 to the n is greater than n for any value of n bigger than or equal to 1, or we could say for any natural number n. So, write your base case, write your inductive hypothesis. And we'll see what we can do. This one I might need to reference.